I'll just begin by introducing myself. I'm Gordon Edwards. My background is as a mathematician. I was a professor of mathematics and science at Vanier College until my retirement. And I've been a nuclear consultant, a consultant on nuclear issues for over 40 years for both governmental and non-governmental organizations. I'm primarily an educator, and so I try and just demystify the subject so that people can understand what the issues are and help them be able to formulate a more informed position on those issues. So I'm talking about uranium, its uses and its dangers, and this will use some black and white photographs by Robert Del Tredici with a little typo there for photographs. The most important thing to know about uranium, it is the key element in all nuclear fission technology. Without uranium, there would be no nuclear weapons of any description, and there would be no nuclear fission reactors. So it is really a key to the nuclear age. In fact, uranium is the only material naturally occurring on Earth that can be used to make an atomic bomb. Now, radioactivity itself was accidentally discovered in 1896 by Henri Becquerel, a scientist in Paris, France, who was very interested in things that glow in the dark. He found that rocks containing uranium or thorium give off an invisible energy that can expose a photographic plate, even one that is shielded from the light by thick black paper. And so this was an amazing discovery, because how can a rock give off energy? You can't see or hear or sense radioactivity, but if you put a rock of uranium ore in a device called a cloud chamber, you can see the energy coming off of that rock by observing the tracks that are left. These are condensation tracks left by the radioactive emissions. Now, the most amazing thing is that these tracks, these emissions are being given off 24 hours a day, 7 days a week, and it has been going on for millions and millions and millions of years without stopping. So it's like an endless font of energy coming off this rock. And nobody had any idea where this energy was coming from at the time. Marie Curie, just a couple of years later, she investigated, and she separated the uranium out of the rock by crushing it up and dissolving it. And when she separated the uranium, she found that the uranium itself was radioactive, but the byproduct, the crushed rock, was actually far more radioactive than the uranium itself. This was a real surprise to her. And she reasoned that there must be more radioactive elements present in that crushed rock. And she identified two of them, which she named radium and polonium. She named polonium after her native homeland of Poland. And so these were the first real identifications of new elements that are radioactive that had never been observed before. Now, it turns out that when uranium gives off an emission, it actually changes into a different substance called thorium-234. And that is also radioactive. And when it gives off an emission, it turns it into another material called protactinium-234. And when that disintegrates, it turns into another one and another one and another one. And in this way, you get a whole uranium decay chain. Each element has its own half-life. The half-life is how long it takes for half of the atoms to disintegrate and give off those emissions. The half-life of uranium-238 itself is about equal to the age of the Earth, and that's why we still find it in the soil, in the ground. Now, a radioactive disintegration is due to the fact that the nucleus of the atom, every atom has a tiny but massive nucleus, and that's surrounded by orbital electrons. And it's the nucleus where the energy comes from, and that's why it's called nuclear energy. And when a nucleus is unstable, it disintegrates at some moment in time. It will suddenly disintegrate and give off either a particle or a ray, an alpha particle or beta particle or neutron. These are particles, or a gamma ray, which is an electromagnetic ray, an electromagnetic form of radiation, very similar to X-rays, but usually more powerful. And it's at the moment of disintegration that this is most damaging to living cells that may be nearby. because those projectiles, those subatomic projectiles, randomly break molecular bonds, including DNA molecular bonds, and as a result, they do biological damage that can sometimes be repaired by the body and sometimes not. And some of those injured cells may turn out to be cancers or other malformed cells later on. The particles do not generally have as much penetrating power as the rays. So for example, alpha particles won't even go through a sheet of paper. However, inside the body, they're far more damaging than even gamma rays. They're about at least 20 times more damaging per unit of energy, and oftentimes hundreds or even 1,000 times more damaging per emission. The beta particles have more penetrating power, but they cannot really go through the whole body. They can only go a few centimeters in soft tissue, whereas gamma rays have great penetrating power and they can go through a lot, just like X-rays in that regard. Also, neutrons, because they have no electrical charge, they have much more penetrating power than alpha particles or beta particles. So these are different forms of radioactive emissions. You can think of them as a kind of a subatomic shrapnel given off by the explosion of an unstable nucleus. Every unstable nucleus is what we call radioactive. Now, we learned very early on that radium in particular, which is one of Marie Curie's proud discoveries, is extremely dangerous to living things. And in fact, it burns, it gives terrible burns, radiation burns that are very difficult to heal. Becquerel discovered this when he had a sample in his shirt pocket, and it created a very nasty burn on his chest. These girls ingested tiny amounts of radium because they were using radium-based paint in order to paint the dials of watches and other instruments to make them glow in the dark. They can glow in the dark all by themselves without the need for any sunlight or anything because of the disintegrations that are occurring. And these girls started dying from a number of diseases: fatal anemia, which also killed Marie Curie and her daughter Irene; bone cancer. There was an epidemic of bone cancer among these women, which is a very rare human disease, and it was quite obvious that it was connected directly to the radium that was accumulating in their bones. And later on, decades later, the girls who survived the incidence of bone damage ended up with head cancers. These are cancers of the sinus and mastoid, and that was due to radon gas generated in the bones by the disintegration of the radium atoms. So here we come to the radon. Now radon, and this is something many people do not know, that every atom of radon started out as an atom of uranium. In fact, it is directly produced by the disintegration of radium atoms, and radium itself is produced by the disintegration of uranium atoms. Now, radon is the number one cause of lung cancer among non-smokers. And in fact, according to the U.S. Environmental Protection Agency, it kills every year between 10 to 20,000 Americans just by breathing radon in their homes. Radon is a naturally occurring gas. Uranium is a naturally occurring element. And so all of its radioactive disintegration byproducts are also naturally occurring. But it is a very toxic, extremely dangerous material. Now, although radon is a gas, its byproducts are solids and they lodge in the lungs. Now, radon has a half-life of 3.8 days. That means that the radon is rapidly disintegrating. And if you let it accumulate in the basement of a home, for example, the so-called radon daughters or radon progeny build up in the air along with the radon gas. And so stagnant air is worse than fresh air because it is given a chance for the disintegration byproducts to build up, so that when you breathe in the radon, you're also breathing in all those other products as well, particularly the polonium isotopes. Polonium is extremely toxic. And in fact, 85% of the lung dose from radon is really from the alpha-emitting polonium atoms, which are also radioactive and also disintegrating and giving off these alpha particles. Here's another example. Polonium, the other proud discovery of Marie Curie, is extremely toxic. In fact, it's probably the most toxic element that occurs naturally on Earth. It is chemically similar to potassium, and so it attaches itself to red blood cells, and it goes throughout the body, damaging soft organs. Victor Alexander Litvinenko was an ex-KGB agent who ran afoul of Putin, and Putin apparently ordered his death. And so two Russian agents came to London and put a small amount of polonium in his tea, and he died a very gruesome death as a result of polonium poisoning. According to the Los Alamos nuclear laboratories, polonium is 250 billion times more toxic than hydrogen cyanide, which is one of the fastest acting deadly poisons that we know of a chemical nature. That's a pretty astonishing number, and it's one of the things that is hardest to wrap your mind around when talking about radioactivity and nuclear matters generally, and that is that the energy levels are millions of times greater than what we normally see in chemical reactions. According to the American Health Physics Society, that same substance, polonium-210, is probably the cause of up to 90% of the deaths attributed to tobacco smoking, which includes lung cancers, heart attacks, and strokes. We know that, of course, a couple of 100,000 people in the United States of America, for example, die every year from the consequences of cigarette smoking. So if polonium-210 is responsible for 90% of those, then we're talking about a real killer. That previously I said that radon is the principal killer of non-smokers in terms of lung cancer, the principal cause of lung cancer among non-smokers. Well, here we see that polonium-210 is perhaps the principal cause of lung cancer among smokers. Now, alpha radiation is not a very penetrating form of radiation. In soft tissue, it'll only go a few micrometers. In fact, only a few cell diameters, really. And so what we have here is a photograph of tissue in a microscope. This is from the lung tissue of an ape with a small alpha-emitting particle of plutonium lodged in the lung. And what you see, that star shape in the middle, are really the tracks of alpha particles over a 48-hour period. So the camera lens was left open for 48 hours, and you can see the tracks of those alpha particles, which you can only see them because of an emulsion that was used so that you could make those tracks visible. Normally, of course, they're completely invisible. Now, the damage that is done is at the cellular level, but those cells can become precancerous, and as much as 20, 30, 40 years later, the people so exposed can develop lung cancer. And in fact, there is a latency period of about 20 years for lung cancer, so that the increase in lung cancers that is observed among people exposed to particularly high levels of radon gas is not observed really until 20 years. And once you start seeing an increase in incidence of lung cancer after 20 years, that incidence continues to occur year after year following that 20-year latency period. So it's kind of subtle, because it, just like cigarette smoking, people don't smoke a cigarette and then fall over dead. And so for a long time, people didn't realize how dangerous cigarette smoking was. We now know that a lot of that danger is due to minute amounts of polonium-210 in the cigarette smoke, which also goes into the blood and consequently causes cardiovascular diseases. Each spike here is the track of an individual alpha particle, as I said before. Now, here is a 10-meter high wall, which behind that wall is a whole lake of 70 million tons of what are called uranium tailings. These are the byproducts of uranium mining in the Elliott Lake region. This happens to be the Stanrock tailings pile, photographed by my friend Robert Del Tredici. And all of that sand contains radioactivity in it, the radioactive leftovers from uranium mining. Uranium mining is only interested in extracting the uranium, but the uranium is only the top of the decay chain, the so-called decay chain. All the materials below uranium in the decay chain are left behind in the tailings. Consequently, 85% of the radioactivity in the ore is left behind as radioactive waste for future generations to deal with. That includes all the radium, all the radon generating material, the polonium, and radioactive lead-210. These are constantly being replenished by the disintegration of thorium-230 atoms. Thorium-230 is one of the decay products of uranium with a 76,000-year half-life. And what that means is that in those tailings, you'll have to wait 76,000 years before you see the radium levels or the radon levels or the polonium levels. Any of those will not go down by half until after 76,000 years. So it means that effectively these radioactive wastes have a 76,000-year half-life. So when the uranium is extracted, most of those decay products are left in the mill tailings as radioactive waste and as a perpetual challenge. They will stay dangerous for hundreds of thousands of years. Generally, one half-life only cuts it down by half. 10 half-lives will cut it down by a factor of 1,000. So that means 10 half-lives would be 760,000 years. Multiply it by 10, and that tells you how much it takes to go from, let's say, trillions of becquerels to billions of becquerels. That's 1,000 times smaller. And then from billions of becquerels to millions of becquerels, that's another 1,000 times smaller. So every 10 half-lives, you get a reduction by a factor of 1,000. Now, the mill tailings hazards are due to the fact that, first of all, there's the gamma radiation, which can be dangerous for anybody on the tailings. And by the way, when these tailings are abandoned, you have people going picnicking on them. You have kids riding bicycles on them. You have people just simply strolling on the tailings because they look completely inoffensive. They don't look harmful. And as a matter of fact, companies think it's wonderful stuff. It looks like sand. And if you don't know it's radioactive, you'd say, well, gosh, we could make cement with that. We could use it as foundation fill. We could use it in construction. And how are people supposed to know that it's dangerous? It just looks like a great body of white sand that you can just cart away. And in fact, thousands of truckloads of this material has been used in construction in many, many different localities. But in addition to the gamma radiation, there's the radon gas, which is being given off all the time. And the radon emissions are 10,000 times greater than they would be from the solid material before it was ground up. By grinding it up, you increase the radon emissions dramatically. And then you have dust blowing around in the air, and you have seepage into the groundwater, uranium and arsenic, for example. But one thing I'd like to mention about the radon is that when the radon gas is given off from the tailings pile in large amounts, it's 7 times heavier than air, and so it'll travel, you can do the calculation yourself, it'll travel about 1,000 miles in a 15-mile-an-hour wind, breeze, and as it drifts across the landscape, it deposits radioactive fallout on the ground below. All those radioactive solid materials, including the polonium isotopes, become radioactive fallout, which enter into the vegetation and the water and enter into the food chain. They have found, for example, in the Northwest Territories of Canada and in Nunavut, the caribou have much higher levels of polonium-210 in their bodies than animals down south. And that's because they eat a lot of lichen, and lichen take their mineral nutrition directly from the air. And in that mineral nutrition includes the fallout from not only nuclear testing, but also the fallout from radon gas emission from uranium deposits, uranium tailings deposits. So pollution from the nuclear fuel chain is like all types of pollution. It's radioactive and chemical particles and gases which contaminate the land, water, plants, animals, and people over a very, very, very long period of time. And it's kind of unremitting. If the tailings are disrupted by human activities or just by natural forces, and they are spread abroad, then they themselves become sources of those other radioactive byproducts. So they become, you're actually spreading the source when you spread the tailings. Lately, not just lately, in recent decades, and in fact, this goes back 40, 50 years or so, they've said, well, instead of bringing the ore to the surface and crushing it up the way we have done most of the time, and that's what's been done in Canada almost exclusively, you could use something called in situ leaching, and this is where you pump down into the ground um, either a strong acid like sulfuric acid or a strong caustic substance, depending on the chemistry of the rock, and also solvents to dissolve the uranium. And then you could pump that pregnant solution, they call it, back up to the surface and use that as your source of uranium, that you chemically extract the uranium from that solution. But the difficulty here is that the gas, the radon gas, is extremely mobile, and so you get large radon emissions. And remember, the radon emissions lead to radioactive fallout of its own, so that you are spreading radioactive materials from deep underground. Even by using this process, you're not leaving it all underground. You are leaving the bulk of the crushed rock underground, indeed. But you're also leaving those acids and solvents underground. And what are the long-term consequences of that? Where does that go? And what does it do to the groundwater? What does it do to the rock itself over a very long period of time? I have to admit that I myself have not studied very closely the particular dangers associated with in situ leaching, but I assure you that it is not problem-free by any means. Now, when they do this in situ leaching, they don't just inject it at one spot, they inject it at multiple spots. So they could have hundreds of places where they inject these solvents, and then they pump it up to the surface through other wells, and they also have monitoring wells, which are not shown here in this diagram. And potential hazards of in situ leaching, well, here are some examples from places where it was done years ago. In Königstein, Germany, for example, there were 100,000 tons of sulfuric acid injected with leaching liquid. 1.9 million cubic meters of leaching liquid is still locked in the rock pores where the ore was located, and 0.85 million cubic meters is circulating. It's moving through the ground. It's very highly contaminated with radioactivity and also with non-radioactive heavy metals. Like cadmium levels are 400 times the maximum permissible for environmental reasons. Arsenic 280 times, nickel 130 times, uranium itself, again, sorry for the typo, 83 times, and so on. So you get a lot going on underground, which is going to be problematic for future generations for a long time to come. And remediation of those problems is difficult, if not impossible. Now, in Czechoslovakia, they had a similar situation, which is even worse. In this case, instead of 1.9 million, they had 28.7 million cubic meters of contaminated liquid contained in a leaching zone, which was originally about between 5 and 6 square kilometers. But this is spread out beyond the leaching zone, both horizontally and vertically underground, contaminating another area of 28 square kilometers and 235 million cubic meters of groundwater. So these materials carrying the radioactive byproducts with them are migrating underground. And what do they do to the groundwater and to the wells that farmers or citizens might be using for drinking water or for irrigation even? Now, all of this is pretty mind-boggling in terms of just the radioactive properties of uranium and its byproducts. But in 1938, around Christmas time of 1938, a whole new chapter began when they discovered nuclear fission. Scientists in Germany were playing around with a thing called a neutron. They were shooting neutrons at uranium samples. And they discovered, much to their amazement, that they split the uranium atom and released an awful lot of this nuclear energy all at once. But when the uranium atom is split, it doesn't just disappear, it splits into fission products. Now, obviously, this does not happen when you have uranium mining. This happens when the uranium is taken away from the mine and used either in bombs or in nuclear reactors. So this is not associated directly with the uranium mining, but it is an ultimate product of uranium mining if you take the long view. So a subatomic projectile called a neutron starts a nuclear chain reaction by splitting one uranium atom, but also giving off more neutrons. And you see those more neutrons at the bottom, they trigger more fissions, and so the energy release is multiplied enormously. And that can either give you an atomic bomb if it's uncontained, or it can give you a steady supply of energy in the form of electricity from nuclear power plants. But the two broken pieces of the uranium atom are, in fact, hundreds of new varieties of radioactive materials which were never found in nature, most of them, before 1939. And these materials are called the fission products, and they are the primary constituent of the so-called high-level radioactive waste. Now, because of the discovery of fission, our government got involved with the UK and with the USA. And in 1943, we signed a secret accord called the Quebec Accord in Quebec City that the three countries would cooperate in building the world's first atomic bombs. And the reason why Canada was included was because we had the uranium. We had uranium left over from radium mining. Back in 1931, there was no use for uranium. They hadn't discovered fission yet, but they were using radium for a variety of good reasons and for a variety of bad reasons. Unfortunately, the radium turned out to be so toxic that by the end of World War II, radium had no market anymore. It was too dangerous to use because it had killed so many people. Nevertheless, the leftovers of radium mining are uranium, because uranium is what produces all the radium atoms. So when you have a radium mine, you automatically have leftover uranium, and that's what Canada had, and that's what they needed for the atomic bomb. Here is one uranium bomb. If you doubt the power of uranium, just one uranium bomb, a couple of tens of kilograms, dropped on a single city, Hiroshima, on August 6, 1945. Look at the devastation. So you can just see how much energy there is locked up in those uranium atoms. And of course, that's what led to uranium mining in Canada, really, was because of this weapons use. So all uranium in Canada up until 1965, virtually all of the uranium mined in Canada went into the bomb program, went into the US bomb program. In 1965, Prime Minister Pearson declared that we would stop selling uranium for military purposes and only sell it for civilian purposes. So from that day forward, the uranium traffic was aimed at non-military contracts. But the first uranium mine was right up at the very top of this picture at Great Bear Lake, just about 100 kilometers south of the Arctic Circle. And that's where the radium came from. It's a place called Port Radium, and that's where the uranium leftovers came from. They were all shipped down to a little town on Lake Ontario called Port Hope. And there's a documentary film that has now been made with CBC sponsorship called Atomic Reaction, which documents the role of Port Hope, Ontario in processing almost all of the uranium. Most of the uranium that went into the atomic bomb project was processed at Port Hope, Ontario. And during the Cold War, that uranium continued to be processed throughout the Cold War period. Now, there were two bombs originally used in 1945. Little Boy was a uranium bomb, highly enriched uranium. Fat Man was a plutonium bomb. Now, plutonium is not found in nature in meaningful quantities. In order to make a bomb, you can't just use natural uranium, you have to enrich it. It turns out that there's one type of uranium, uranium-235, that's the chain reacting variety. And you have to increase that concentration of that chain reacting variety in order to get a bomb. And so you get from low enriched uranium or natural uranium all the way up to high enriched uranium. And at about the 20% level, when you get 20% uranium-235, that's where you begin to talk about highly enriched uranium, and that's weapons usable material. Now, some of the reactors that they're now proposing, for example, in New Brunswick, the arc reactor is going to use not 20% enriched, but only about 17 or 12% even enriched. But it turns out that once you get past about 12%, between 10 and 20%, we now know that that stuff is also weapons usable. So we're starting to traffic more and more in material that can be used directly in bombs. Whereas natural uranium that we use in the CANDU reactors today, you can't make a bomb out of that stuff. It has to undergo enrichment first. Now, plutonium is something else. It's a uranium derivative. When you put uranium into a nuclear reactor, I told you that U-235 is the type that splits. Well, uranium-238 actually is 99.3% of natural uranium, and it does not split. But when it's hit with a neutron, a stray neutron, it turns into a new material called plutonium. And plutonium is the raw material in all the nuclear arsenals of the world. Plutonium is the principal nuclear explosive. Not the only one. The other one is highly enriched uranium. And here is a chart showing the mills, the uranium mills in Canada, and which of them produced uranium for bombs and which of them produced uranium for peaceful purposes. And you can see there was a lot of activity there in terms of bomb connections. The first place, as I told you, was the Satu Dene village of Delaney, Great Bear Lake. Across that huge lake was Port Radium, and that's where they mined the first radium. These, the men from the village were used as, they called them coolies, and they carried sacks of uranium ore on their backs. First of all, they carried sacks of radium ore, and then later uranium ore. Nobody told them this stuff was dangerous, and nobody even provided them with showering facilities or protective clothing or gave them any kind of warning about it. These are leftover sacks, burlap sacks that were used to carry and many of the women of the village would take these sacks and try and reuse them because they don't like to waste, right? They like to recycle and reuse things, and it's just a part of don't waste not, want not. And nobody told them that this stuff is dangerous. And so they took them into their homes, and as a result, they got a lot more radon gas and radium dust than they would have experienced otherwise. Some people think that, well, they didn't know the dangers back then. Not true. They did know the dangers because they already knew that people had been dying from radon gas. By the 1930s, it was well established in the scientific literature that thousands and thousands of underground miners of all kinds have been dying of radon gas exposure. And it was known in the 1920s about the bone cancers. So this is a publication from 1931 from the Canadian Department of Mines saying that indeed lung cancer, bone necrosis, and rapid anemia are possible diseases due to deposition of radioactive substances in the cell tissue or bone structure of the body. So it was in fact well known. This document from 1931 was for the benefit of the scientists in Ottawa who had to assay the ore. They were cautioning the scientists to be very careful in handling even small quantities because you could endanger yourself. But these warnings were not given to the Indigenous people, nor to the miners who worked in the underground mines. The warnings were only for the scientists in Ottawa. Now, Port Hope, Ontario is where all of this material went to, and we have the Cameco uranium conversion plant situated right on the harbor of Port Hope. And right now, we're in the middle of a more than $2 billion radioactive cleanup of this town, involving more than 2 million cubic meters of radioactively contaminated soil that's being excavated from homes, from schools, all throughout the town. It's a long and sordid history, which is told in that film, Atomic Reaction, which you can find on GEM TV if you want to go looking for it. We in Canada, after World War II, we decided that we didn't want to actually make bombs, but we did like to use the energy, and so we built CANDU reactors. And this is how a CANDU reactor works. In the core of the reactor, you have the fuel, the uranium fuel. Fissioning of the uranium fuel releases a great deal of heat. That heat is used to boil water. So basically, a nuclear reactor is another way of boiling water, just like a coal-fired plant or an oil-fired plant to produce steam. And the steam is produced in the steam generator, and that is used then to spin the blades of a turbine and generate electricity. But in the process, all of those split uranium atoms are left in the core as fission products, and the radioactivity spreads throughout the cooling system. Now, this is from the Porter Commission in 1978. They mentioned the extreme lethality of a freshly removed spent fuel bundle such that a person standing within a meter of it would die within an hour. That's from the gamma radiation. But also the materials inside are alpha emitters and beta emitters, and they leak out through tiny pinholes and cracks. And severe fuel damage will cause massive leaks. So the fuel does suffer corrosion, distortion, and embrittlement in the reactor. This man is holding up a simulated pellet of uranium, and he's saying, small wonder, it's an ad from the Canadian Nuclear Association. He's saying, isn't it wonderful how this small pellet of uranium can produce as much energy as a carload of coal and yet not emit carbon dioxide into the atmosphere? These are the two great benefits of nuclear energy, is that it's a very concentrated form of energy, and it doesn't release carbon dioxide because they're not combustion. But what he doesn't say is that once that fuel pellet is used to generate electricity, it will never be handled by human hands again, and it will remain dangerous, and it must be kept, you have to keep an eye on it for the next 10 million years, because that's how long it's going to remain dangerous through all of the byproducts caused by nuclear fission. Here's the face of a Candur reactor loaded with fresh, unused fuel bundles. That man would be dead if this reactor had ever operated. But this is a reactor which has never yet operated. It's a Darlington reactor that hasn't yet been started up. So a man can stand there without protection and not get a lethal dose of radiation. After being used in the reactor, the spent fuel, the irradiated fuel, has to be put into a deep pool of water, circulating water, for about 10 years to prevent it from spontaneously overheating. Now, the fact of the matter is, radioactivity is a form of energy, and the radioactive fission products give off energy through the disintegration of the atoms, which cannot be stopped. And that generates heat. And in fact, the heat from the disintegration of the radioactive atoms in the core of the reactor are enough to melt the entire core of the reactor into the ground. That's what happened at Chernobyl. That's what happened at Fukushima. That heat gradually calms down, but even when it's buried underground, it continues to generate heat for a long time. And according to Atomic Energy of Canada Limited, the rocks are heated up by the radioactivity of the waste if you bury them in a rock formation. And it'll take 50,000 years for those rocks to return to their ambient temperatures. That's how long, that's called the thermal pulse of the radioactive waste. This is just one of the dry storage containers at Pickering. It weighs empty 60 tons, full it weighs 70 tons. So it's a 60-ton container designed to hold only 10 tons of radioactive waste. The reason they have a seal at the top of that container, that's called a safeguard seal. That's to ensure that nobody is getting inside and getting out the plutonium. So each one of these containers would have enough to make about 6 or 7 atomic bombs. So that's why the safeguards are applied, to make sure that the newly created plutonium in the used fuel is not used for malicious purposes. Now, I think I will just simply stop there. This was a international campaign for a global ban on uranium mining that took place at the International Uranium Congress held in Quebec City. And these people were attendees of the conference from all over the world, and they're posing there in front of the National Assembly, Quebec's National Assembly, asking the politicians to consider the consequences, the long-term consequences of uranium mining. We demand a worldwide ban on uranium exploration, mining, milling, and processing, as well as the reprocessing of nuclear waste. That was a small part of the declaration that came out of that particular event in 2015. The one thing I would like you to take away from this is that uranium is not just one substance, it's actually hundreds of different substances. It's a kind of a shapeshifter. In the ground, it changes into things like radon, radium, and polonium, which are very dangerous. In a nuclear reactor, it changes into things like iodine-131, cesium-137, strontium-90, which are fission products, which are also very dangerous. And it also produces the so-called transuranic elements, the elements that are heavier than uranium, such as plutonium, americium, and curium. And that gives rise to the concern about spread of nuclear weapons. When you talk about uranium, you really are talking about not just one substance, but many. If it were not for all those byproduct substances, it wouldn't pose such a conundrum. These girls are Kazakh women, young women, who are just discovering on the day that this photograph was taken by Robert Del Tredici, they were just discovering for the first time that the Techa River that flows past their village decades ago, they had dumped high-level liquid radioactive waste into that river. And that was the reason why there was such a rash of diseases downstream from the dumping spot. Bob likes this picture because he says we're all kind of in the position of these women, trying to worry and wonder what the future holds in store. We must all make our best efforts to ensure that radioactive waste do not contaminate the air we breathe, the food we eat, the water we drink, or our reproductive cells. And indeed, nobody wants that to happen, nobody in the industry or outside of the industry, but things happen when they're not properly done and when they're not properly attended to. And unfortunately, we still do not really have a proven safe solution in the very long term for the long-lived radioactive waste at the high level. Thank you very much, and maybe we'll have time for some questions and answers after this. My curriculum vitae is online. If you go to ccnr.org is the CCNR website, and then you put /GE_CV.pdf, and that's my CV. So I graduated from the University of Toronto in 1961 with a gold medal in mathematics and physics. I originally wanted to go into nuclear chemistry. I had a cousin who was in nuclear chemistry, and I found it really, really fascinating and interesting. 1974 was the year in which India exploded its first atomic bomb using plutonium from a reactor that Canada gave them as a gift. That kind of shocked a lot of people. And at the same time, that same year, I discovered for the first time that the town of Port Hope, well, the elementary school, St. Mary's Elementary School, had to be evacuated because of the radon levels in the cafeteria. So that's when I got involved in the Canadian Coalition for Nuclear Responsibility. I was concerned for the fact that people were being told what the advantages of nuclear power were, but they were not being told much about what the disadvantages are. And I figured that you need to have a balance. You need to look at all sides, and you need to weigh the costs and the benefits with each other.
Another question, Gordon. What happens to the cooling water where the radioactive bundles are stored?
First of all, the cooling water doesn't get extremely radioactive unless there's very, very bad damage to the bundles. But normally there is always a little bit of leakage, and so they have what are called ion exchange resins, which are filters, high-capacity filters that filter out the radioactive materials. Those filters themselves become very dangerous radioactive waste, which has to also be stored for a very long time. We're talking about hundreds of thousands of years. For example, carbon-14 is one of the materials often found in those filters, and it has a half-life of 5,700 years. There's also smaller amounts of, even plutonium is found in those filters, and that has a half-life of 24,000 years. The other things have half-lives of hundreds of thousands of years, so they become very long-lived waste as well. But the water itself is continually filtered, and they try to remove, they can't remove certain things. For example, tritium, radioactive hydrogen, because it's chemically identical with ordinary hydrogen, it makes water molecules which are radioactive, and you can't filter those out. And the result is you get a lot of tritium buildup in water. Some of you may know that in Fukushima, for example, they had over 1 million tons of radioactively contaminated water, which they're now gradually dumping into the Pacific Ocean. And both China and Korea are very much opposed to this, and they have boycotted the fish products from Japan because of this dumping that is going on. And the problem is that they can filter out a lot of things, but they can't filter out the tritium. And so there's a great deal of tritium in that water.
Gordon, another question. Has anyone been able to safely store spent fuel rods so that there's no radiation outside of the storage area?
It's very difficult to get things down to zero, but certainly they have very robust, very strong storage methods, which are tightly sealed and which generally prevent leakage of various kinds. The gamma radiation is quite penetrating, and so you do get a bit of gamma radiation coming off, and a judgment has to be made as to how much is allowable and how much is not allowable. Even when they transport the high-level waste, the gamma radiation really can't be totally shut off, so a decision has to be made, like all the people along the route that the truck is traveling will get very small doses of gamma radiation, but the damage of radiation is accumulative over years, and so you have to worry about what that is going to work out to be over a long period of time. If somebody were to, for example, if there were to be actual spillage of the contents, then you would be faced with an emergency that would have to be dealt with. But generally, they try and provide enough shielding to give them, that is the authorities, satisfactory assurance that they think it's okay to allow that small amount of exposure.
Could you please give an outline of the health risks for uranium as it occurs naturally in groundwater?
Well, uranium is a heavy metal, and like all heavy metals, it's dangerous. All these heavy metals are dangerous, and uranium is no exception. It's particularly, it's a renotoxin, and it damages the internal organ accordingly. The actual chemical toxicity of uranium is generally considered to be either on a par with or greater than the radioactive toxicity. Because uranium has such a very long half-life, 4.5 billion years, that means the atoms are disintegrating very slowly. And as a result, the chemical toxicity is of equal concern, if not more concern, than the radioactive toxicity. But then you have to bear in mind that uranium is not just one material. It's many materials. And so along with the uranium, you have all these other materials, which are all of them, each one of those decay products is far more radioactive and far more dangerous than the uranium itself. So when people say that uranium is not the most dangerous of radioactive materials, they're certainly correct in saying that, but that's ignoring the fact that uranium spawns a multitude of very dangerous radioactive materials, which have killed an awful lot of people.
Gordon, could you discuss the exploration that exposes uranium, even if you're looking for other minerals, and what risks that would cause?
Well, the exploration is a tricky thing because if you penetrate an ore body, bearing in mind that you have built up all these decay products in the ore body, it is generally considered that when you have a very old uranium deposit, the actual radioactivity is measured in something called becquerels. A becquerel means 1 disintegration per second, 1 atomic disintegration per second. It turns out that the number of becquerels of uranium and all of its byproducts are more or less exactly the same. And that's because we've achieved something called equilibrium over the centuries underground. Now, so when you bring up the uranium to the surface, you're bringing up all those uranium byproducts as well, and they all have as much becquerels as uranium itself. So, but they're far more toxic because they're disintegrating a lot faster, and they also they more avidly reach different parts of the body. Radon gas, for example, is very easily inhaled. Radium goes to the bones. It's similar to calcium in that regard. And each one of these elements has its own chemistry and therefore its own pathway through the environment and through the human body. So when you explore for uranium, even if you're exploring for something else and you happen to intersect a radioactive ore body, you provide pathways for those radioactive materials to come to the surface, particularly the radon gas, which of course is very mobile. And that radon gas brings with it, as I said before, actually about half of all the uranium decay products are byproducts of radon gas. So when the radon gas comes to the surface, it deposits radioactive isotopes of bismuth, radioactive isotopes of lead, radioactive isotopes of polonium. These are deposited in the vicinity. And of course, in enclosed spaces, they're particularly dangerous, as I mentioned before. So I would mention, for example, one of the famous studies that has been done is Newfoundland. In Newfoundland, they had what are called fluorspar mining. Now, fluorspar is not radioactive, and it was not uranium mining. However, the Newfoundland fluorspar miners suffered an atrocious amount of lung cancer caused by radon gas. Now, that radon gas did not come from the fluorspar. It came from uranium deposits, which were not where they were digging. But the radon gas migrates very easily, and it migrated into the cavities where the Newfoundland fluorspar miners were working. And so they ended up getting a lot of lung cancer caused by radon. And that radon had been produced by uranium, but that uranium was nowhere to be seen in the workings that they were working. Same thing in Sweden. They had iron workers, underground iron workers, who also suffered a high mortality from radon gas, not from those deposits, but from adjacent deposits some distance away. Alpha radiation is something that oftentimes fools people because it's really quite hard to measure. Radiation monitors don't always pick it up. There were 500 workers at Bruce. These are just ordinary workers, pipe fitters and plumbers and so on, and welders. 500 workers who were exposed for 3.5 weeks to alpha-emitting dust that they were breathing in every day, and nobody noticed for weeks that they were getting this radioactive exposure because it was not registering on the radiation monitors. But even though alpha radiation is difficult to detect, it is far more damaging than the other forms of radiation. For instance, every becquerel of plutonium radiation, which is alpha, is approximately 18,000 times more biologically damaging than a similar becquerel of radioactive hydrogen, tritium. So comparing a becquerel with a becquerel, you'd think they would be more or less the same. Not so. The becquerel of plutonium is about 18,000 times more biologically damaging than that of tritium. And by the way, this is using procedures that the CNSC, the Canadian Nuclear Safety Commission, uses as well.
Stephen Starr, would you please speak up?
Hi, Gordon. I think you skipped over a slide right at the end there that showed the longevity of the decay products. Would you mind showing that, or is that too complicated?
When people try to get the video of the presentation, I will also include a link to my slideshow, and it will include that slide as well. That slide comes from the 1978 report from the Royal Commission on Electric Power Planning in Ontario on nuclear energy in Ontario. And it shows a graph where the time scale is 10 million years. And it shows how the radiotoxicity, that is, what is radiotoxicity? Radiotoxicity is what happens when you ingest radioactive materials. Instead of just being exposed to them externally, suppose it's in the food that you're eating or the water you're drinking or the air you're breathing. And so you inhale it or ingest it into your body, and it'll stay for a while in your body. It'll stay for a period of time, a residence time. That's what we call radiotoxicity. How radiotoxic is it? And that radiotoxicity, it does diminish with time sharply, but after about 50,000 years, it reaches a low point. And then what the Royal Commission on Electric Power Planning pointed out is that the toxicity after that time, it actually goes up again. It increases rather than decreases. And the reason why is because of all these changes that are happening. When the atoms disintegrate, they don't disappear, they change. Sometimes they change into things that are more toxic than what they were to begin with. Suppose you had a little glass vial, only this big, that was full of pure radon gas, pure radon gas. If you just let that radon gas sit in that vial for an hour, in an hour, it'll be 6 times more radioactive than it was to start with. And why is that? That's because most of the radon is still there, but the part that has disintegrated has turned into far more radioactive materials, the polonium and the bismuth and the lead isotopes. And these are equally radioactive with the radon. So the radon vial actually becomes more radioactive, not less radioactive, for the first hour. Now, after about 3.8 days, then the whole thing will diminish by a half, because that's the half-life of radon. So this is what happens with this long-lived waste also. Things which were there originally with a certain toxicity, sometimes they change into things which have an even greater toxicity.
Leona, are you still with us?
Hi, Gordon.
Hi, Lane. Hello.
Hey, I'm in the U.S., but just internationally, what can people do to take steps to stop all this?
Well, I think that one thing we have to do is stop being hypnotized by the public relations sales job that's going on about nuclear. Nuclear is being presented as if it were a quick remedy to the climate change crisis, and quite apart from the radioactivity, quite apart from the health dangers, this is simply not true. Nuclear power is far too slow to deploy and far too expensive to deploy to make it a reasonable investment. Wall Street, the Lazard firm in Wall Street, compares different energy sources for investors, people who want to invest in energy supply systems. They point out that wind with storage of electricity and solar with storage of electricity are both far cheaper than nuclear. In fact, so much cheaper that the highest estimated cost of solar with storage and wind with storage is much lower than the lowest possible cost of nuclear. So the question is, why would you be putting money into the things which are the slowest and the most expensive rather than the things which are the fastest and the cheapest? And in fact, the International Energy Agency has reported that they expect that in the next 10 years, fully 90% of all of the electricity, new capacity being installed around the world will be renewable. So I think that that's not to say that there aren't problems. That's not to say there aren't difficulties, but it is to say that anybody who tries to tell you that nuclear is a timely or easily affordable option for defeating climate change is not telling you the full truth. It's very important that people weigh many sides of the story and figure out what makes more sense. To me, it makes more sense to invest in the things that are fastest and cheapest first, and then if you need more, to invest in the things which are slower and more expensive later. But the other thing about renewables, by the way, is that they happen to have a payback time which is a lot faster as well. So that wind projects, I've done some research on this, wind projects typically pay themselves off in about a year or less. In other words, they generate enough sellable electricity that you have recovered your investment and you can use that money to build more. Nuclear, on the other hand, takes typically about 10 years or so to build, from conception to building. And then it takes another 10 years before it starts paying itself off, because it first of all has to pay off the cost of what it took to build it. And then you start getting some benefits from it. But that payback time is very slow. That's 20 years down the line. You're really kicking the can down the road when it comes to climate change.
Simon, do you want to unmute, please?
Hi, Gordon. On May 25th, 2025, President Trump decided to contact the Independent Nuclear Commission in the United States to accelerate small modular reactors to 18 months of permit approval. So now that the G7 and other countries are coming to Canada and Alberta this weekend, how should the Canadian government approach President Trump, you know, um, deregulation, uh, and obviously there's going to be a spillover in Canada and how our nuclear industry is going to react to that response. So how do you see the Canadian government responding to Trump's eagerness in approving quick nuclear energy and also small modular reactors?
Boy, oh boy, I would have to be some kind of Houdini to give you the answer as to how to handle President Trump. Unfortunately, our government, I think, is being a little bit spooked by Trump. Bill C-5, which is now being put before the Parliament of Canada, would in fact allow us to put aside most of our procedures, most of our environmental assessments, most of our deliberative mechanisms in order to fast track and rush ahead with projects like nuclear and like pipelines and all kinds of, our Prime Minister Carney is wanting to imagine that Canada can become an energy superpower. And of course, these things are very tempting visions for people who are in the business of wielding power and maintaining power and preserving power and helping their country to achieve power on the world stage. And I don't mean to denigrate the aspirations of Mr. Carney, but I think that this is not a mandate that all Canadians that I know of would approve of. And I have written a letter to Mr. Carney just this morning, in fact, urging him not to follow the Trump line by setting aside laws that were created precisely to protect people and the environment from irreversible dangers that can follow from certain procedures. But I believe that we in Canada are being spooked into doing something very similar in a way to what Trump is doing. The difference being that at least we're going through the Parliament. But the parliamentarians, are they themselves sufficiently well equipped to judge these matters in a single vote? We're at a crucial time in our history indeed. And I do think that that Canadians, now more than ever, I think Canadians have to realize that if democracy is to be meaningful, it's got to be more than just voting for people. It's got to mean making your voices heard on all major decisions that are affecting our children, our grandchildren, for generations to come. Mr. Carney, please do not follow the lead of President Trump in setting aside the law, setting aside the legal mechanisms that were established with good reason, just for the sake of expediency. And that's what Bill C-5, to me, seems to do. And I particularly point out that the Indigenous peoples of this country, who have been deprived of economic and political clout through a colonial marginalization, that their only friend really has been the courts. The courts have stood up for them and said, yes, treaties are in fact legally binding. You can't just sign a treaty and then ignore it. You have to abide by the terms of that treaty. And even though these Indigenous people may not have the power to dethrone you or the economic power to buy you, nevertheless, their rights have to be respected. They are guaranteed in these treaties that are legally binding treaties. Well, I think that Bill C-5 basically annuls that. It basically says that the Indigenous people's rights are taken away because those legal mechanisms are gone. So therefore, I do think that people have to be careful that they're not making a big mistake in pursuing a certain course of action, which is going to have repercussions for many generations to come.
Mike, would you like to lower your hand, please, and unmute? Thank you.
Hi, Gordon. This is Mike Bohr here in Ontario. As you are well aware of, you already know C-5 is being discussed and possible amendments being made to that. In Ontario, we have Bill 5, which has already been passed, and it does the very same things and even worse than C-5. With that, the call for saying that there's a uranium shortage that is going to be need to be made full now. They're saying that they're going to increase uranium mining rather than decreasing uranium mining. What can be done to stop this other than just writing these letters? Because they seem to be ignoring letters and that. I mean, I've been a big proponent of sending in letters, and there's hundreds and thousands being sent, and they're just put aside. We're going to be snowed under with uranium and the waste byproducts, and they're already talking about a second repository needed in northern Ontario. That's because of the tons and tons we are already sitting on, with 14 or 15,000 tons alone at the Pickering nuclear plant that have no further prospect of even being moved to there. Would you like to comment on that, please, Gordon?
Well, that's an awfully big question, of course, Mike, and I appreciate your concern, and I share it. I think many Canadians are appalled to see Americans, our good friends and neighbors, willing to sort of throw out democratic traditions for the sake of what they think is going to benefit them in the short run, and may not even be a benefit in the short run. I don't think we should follow suit here in Canada. I think we have to realize that our democratic traditions, democracy is a lot more fragile than many of us have been led to believe. And once you lose it, it's gone. And we have to really fight to preserve it. And I think we tend to sit back in our easy chairs and relax and say, all's well with the world and people are looking after my welfare. Well, such is not the case nowadays. I think that nowadays people really have to become involved directly. Now, whether that's organizing demonstrations, whether that's voting, developing some kind of organized mechanism to deal with it, I don't know, but I believe that it's a cause that really has to permeate our thinking in a way that has not been necessary before. Because if we don't step up and make our will known, what we have, I believe, if I may say so, I believe that we have a lot of collective consciousness about the problems we're facing, but we're lacking collective will. And collective will is a lot harder than collective consciousness. It means we really have to work together on this. And I am, to tell you the truth, I'm not great at it, the organizational aspect of it, but some people are. And I think we have to turn to those people who are good leaders in that regard and say, tell us how to be more effective in making our voices heard, but more importantly, not just making our voices heard, making our will felt. If I may just say that I've often made the point with some of my friends that people complain that, well, you know, the media, they don't report even-handedly. Of course, our media has lost a great deal of independence in the last few decades. You know, independent media has suffered greatly and is still laboring. So trying to get a truly balanced forum for these points of view is very difficult. But I think about the million people who marched in New York City against the nuclear weapons in Eastern Europe, Western Europe rather, and how that almost brought President Reagan and Gorbachev almost to the point in Reykjavik of deciding to abolish all nuclear weapons. They came very close. And it was only the panic of the military advisors that prevented it from occurring. I also think of the anti-apartheid movement, how without any help from the local, certainly from the South African press, that they were able to overcome, they were able to take away that regime despite great disadvantages. And the same thing with the collapse of the Soviet Empire. You know, these things happened pretty peacefully, pretty non-violently, and yet they were major shifts. Now, whether we've taken full advantage of those shifts is something else, but it's not going to happen by just writing letters. I agree. It's got to be expressed in action, and it's got to be expressed in action which is undeniable. And that means that we really have to put our heads together and figure out strategies for manifesting this collective will that we feel we have. I'm too old for that game myself. I'm going to be 85 this summer, and I think that younger people have got to pick up the. We can help by helping younger people to understand more clearly what those issues are and why they're worth fighting for. But we really have to make a noise if we want to expect anybody to pay us attention. I mean, even babies know that. They got loud voices for a reason. A screaming baby is not usually ignored.
Simon, you've been persistent. I'll let you be the last question.
Gordon, this is just a comment, and perhaps I think, and I've been saying that for years now, we need to go through the courts. And we know that we had these 3 federal courts cases go through, 1 or 2 got successful. So how do we see, or how do you see that bringing forward more court cases against the nuclear industry and nuclear waste seems to me brings some results. So how do you see that?
Certainly, I mean, the native people of Canada, the Indigenous people, I mean, it's only because of the Supreme Court of Canada that they have the duty to consult accepted.
Yeah.
And they've won their rights, their treaty rights were being ignored by the government of Canada routinely. And the Supreme Court ruled, you know, look, this is a legal document. You've signed this thing. You're bound by it. You can't just ignore it. So the courts are very important to justify, but there has to be a law that's broken. The court does not dispense justice. It dispenses opinions about legality. Did you break the law? Did you not break the law? And the difficulty is that we don't have very good laws that we can enforce. So that's part of the problem, Simon. Also, of course, the question of resources, because it costs a lot of money to go through the courts, and they have a lot deeper pockets than we do, even though the pockets they have are actually our pockets.
Exactly.
They're actually picking their money out of our pockets, but we can't do the same thing. We can't pick our own pockets the way they do. So those are the 2 major obstacles. I have a very good friend who actually worked in the nuclear industry for over 20 years and who is totally outraged at what's going on today. Because the fast tracking of these nuclear regulations and basically saying that forget about even you know, just license the damn things and get them built. That's a terrible attitude towards the most dangerous technology we've ever invented on Earth. And I was very upset recently when I testified about the new reactor being planned for Darlington, the BWRX 300, the so-called small modular reactor. I documented in my testimony, and I can send this to anybody who wants to see it, that in order to get this small modular reactor to be a little cheaper so that they can compete with renewables, and they can't compete with renewables even so, but to try to make it cheaper and to try and make it faster, what have they done? They've eliminated 6 different safety systems. They've eliminated safety systems which were considered sacrosanct before, like the emergency core cooling system, the overpressure relief system, or the core catcher. They had a core catcher in the original design in case of a core meltdown. And they said, no, we're just going to eliminate those things, save money, and maybe make it a little faster to license. So I think it is dreadful, because as soon as you travel down that road, you're basically eliminating all the progress that's been made on sensible legislation. But the big problem, Simon, is you've got to find a law that they have broken.
Okay, thank you.
Thank you very much, Gordon, for your time and your knowledge and your willingness to share. And thank you all for joining us. I'm going to end our session. Bye.